Hello and welcome to this video walkthrough of the OCR Gateway Physics Paper 1 from June 2015. This particular video is focusing on the second section, section B, which is all about P2. A little reminder about the equations on page 2, and for this particular section we'll be focusing on these two equations from P2. Question 5. Scientists are worried about greenhouse gases. Look at the simple diagram of the Earth and its atmosphere. There's a good clue here showing you what you need to be talking about. Just here it's talking about the wavelength, the short wavelength radiation from the Sun. We've got the Earth's atmosphere and we've got the Earth's surface. The greenhouse effect helps keep the Earth warm. Explain how the greenhouse effect warms the Earth. So I'm going to box the command word explain. And I'm going to underline the greenhouse effect. I'm going to go back and underline that short wavelength because I think that's important. So looking at my answer, I say that the short wavelength radiation penetrates the atmosphere and heats the Earth. The Earth emits the radiation with a longer wavelength. And that emitted radiation is then absorbed by the greenhouse gases. And of course that is where the Earth warms up. That's how the Earth warms up. So, moving on to the next part of the question, just scroll this up. Part B. Three main greenhouse gases are water vapour, carbon dioxide and methane. These gases can be man-made or produced naturally. Complete the table showing a possible natural cause for each gas. So in our table we have water vapour. A man-made cause for that is burning fuels, and a natural cause would be evaporation from our oceans. Carbon dioxide. Man-made cause is burning fuels, but of course we can have some entering the atmosphere from volcanic eruptions, from volcanoes. And methane, producing fuels produces methane, and natural cause we've got decomposition, or you could have had cattle farming. Part 2. A lot of scientists think that global warming is mostly caused by human activities. A few scientists think that global warming is mostly a natural cycle. Suggest a reason why some scientists think it is mostly a natural cycle. Well, the main reason for this is because the Earth has gone through cycles of warming and cooling at various points in the distant past, including ice ages. So for part 3, each greenhouse gas gives a different contribution to the greenhouse effect. Look at the information about each gas. So you have a table here which lists the greenhouse gases, but it also lists percentage of gas in the atmosphere, how long it lasts, something called the global warming potential, and it's important to realise that that's got to be calculated over a few years, and its contribution to the greenhouse effect overall. Okay, so the global warming potential is for water vapour has not been calculated. Use data from the table to suggest why scientists do not calculate the global warming potential for water vapour. Well, the main reason is because we can see from the table that for water vapour it only lasts a few days, and we can see up here that with the global warming potential you need to monitor it over a few years. So my answer is that the water vapour only lasts a few days, which is not long enough to determine the GWP properly. So moving on to part C, methane has a GWP that is 21 times more than carbon dioxide, but contributes less than carbon dioxide to the greenhouse effect. Suggest why. Okay, so let's scroll up and have a look at the table again. So when we look at methane, indeed it does have 21 times more the global warming potential than carbon dioxide, but its contribution is a lot less. And the reason for that are these two bits of data here. There's a lot less of it in the atmosphere, and you can see that it does not last as long. So going back to my answer for that question, I've said there's less methane in the atmosphere and it does not last as long. So question 6, Dr. Williams shows her class an experiment with radioactivity. She uses 3 different radioactive sources. One is an alpha emitter, one is a beta emitter, and one is a gamma emitter. She uses different thicknesses of sheets of paper between the source and the sensor. So the diagram shows us how the equipment is set up. You've got your radioactive source, you've got some sheets of paper, and then you've got your detector here. So scrolling up, Dr. Williams measures the nuclear radiation from each source using the sensor. Each radioactive source emits only one type of radiation. That's important. This can be alpha, beta, or gamma. Look at her results in her table. So let's have a closer look at the results. So what we have here is we have the thickness of the paper that's been placed between the source and the detector. We have our three sources X, Y, and Z, and going down the columns we have the average count rate in counts per second. So we need to draw some conclusions from this data. So with radioactive source X, what we can see is actually, although there's some fluctuation, this number here isn't changing. It's around 30, and it will fluctuate up and down because basically radioactivity is random. In this particular column, what we have is we have the values dropping very significantly, practically down to 0. And that shows me that this source is being stopped by the paper. So when we get to about 0.4 millimeters, 0.5 millimeters maybe, or 0.6 millimeters, sorry, then we are seeing a vast reduction in this value, and therefore this source is stopped by paper. And then source Z, we can see that it's been affected by the paper. The value is dropping and dropping and dropping as we go down the table, but you can also see that it hasn't gone down to 0. So even at 2.0 millimeters thick, there is some radiation getting through. So just to summarize, the first source of radiation, the paper's having virtually no difference to the actual count rate. Second source, source Y, the paper is stopping the radiation, absorbing the radiation. And in the third source, source Z, the radiation is getting through, but the thickness is absorbing some of it. So the question then asks us, use the data, so let's box that, to identify and explain which radiation comes from sources X, Y, and Z. Comment on how useful each source is for detecting the thickness of the sheets of paper up to 2 millimeters. So, of course, the quality of written communication will be assessed in your answer to this question. So we need to have good grammar, good structure, and it be logically laid out. So here's what I said. Source X is emitting gamma radiation. I know this because the count rate is not changing as the paper gets thicker. I know this because the count rate is not affected by the paper thickness. This would make it unsuitable for measuring the thickness of paper. Source Y is emitting alpha particles. I know this because the radiation is completely stopped by paper. This would make it unsuitable for measuring the thickness of paper. Source Z is emitting beta radiation. I know this because the count rate is decreasing steadily as the paper gets thicker, but the radiation is not stopped completely. This makes source Z the most suitable source for measuring the thickness of paper. So what I've done is for each one, I've identified what the source was, I've stated how I know from my data, and then I've commented on the actual suitability for measuring the thickness. So I've identified, explained, and commented. Question 7. Fossil fuel power stations generate electricity. Nuclear power stations also generate electricity. Many people think that nuclear power stations are a greater risk to people than fossil fuels. Explain why. So I'm going to obviously box that. So why are nuclear power stations considered a greater risk? Well, you could have gone along the route of a nuclear explosion, a terrorist attack, a radioactive leak, all those types of things, and you would have got 1 mark. But the most significant thing that we're going to be worried about if somebody builds a nuclear power plant beside us, or we have to live beside it, is actually radioactive waste. So the key idea is that radioactive waste is active for a very long time. We know that. And of course, if there's any exposure to that radioactivity, it can cause cancer. And that's what people are going to be mainly significantly worried about. Accidents are very rare, terrorist attacks are very rare. This is going to be the overriding thing. So that's what you needed to mention to get the 2 marks. In 2011, there was an accident at a nuclear power station in Japan. This was a very serious accident, but there were no deaths reported. The authorities evacuated the general public from the area. Suggest, so let's box that, suggest other things that the authorities might have done to reduce the risk to the workers and rescue staff. So we've got to suggest other things, okay, other than evacuation. So obviously they're going to have to send some people in there to sort things out. So those people would obviously be using protective clothing and masks. And of course what you would try to do is you would limit the exposure of the workers to the radioactivity, and obviously monitor their exposure, and you can use badges for that, and obviously measurements and all that type of thing. Okay, but the key thing is protective clothing, and you would limit that exposure. So scrolling on down to the last bit, explain how the authorities could decide when the public can return to the area. So again, we've got to explain. Well, pretty obviously you'd have to measure the activity in the area, because otherwise how are you going to be able to make a decision? So we've got to measure the activity in the area, and then of course when it's fallen to a safe level we can allow people to move back. And those safe levels are quite clearly described. It's not necessarily background radiation, but it could be a little bit above that, because our bodies can cope with certain levels of radiation. Question 8. This question is about paying for electricity, part A. Alice checks the information on her electricity bill. She also looks at information about some of her appliances. So here we have a table with some data in it. We have 3 appliances: the cooker, immersion heater and central heating. We have their average power in kilowatts, okay, and then the time they used per week in hours. Now as soon as I see kilowatts and hours, I know that we're going to be calculating the cost of electricity. Habib also looks at the information. He sees from the bill that the price of a unit of electricity is 20 pence. So every unit of electricity, every kilowatt hour is going to cost the consumer 20 pence. Alice says using the immersion heater will cost twice as much as using the cooker. So quickly, we're talking about the immersion heater and the cooker. So it's important to note that at the moment, central heating has not been mentioned. Habib says using the immersion heater will cost nearly £5 more a week than using the cooker. So they're making different claims to how much more the immersion heater will cost compared to using the cooker. Okay, so scrolling down, it says complete calculations to show who is correct. So to calculate the cost of something, we've got to times the energy used, which is equal to the power times the time, and then obviously times it by the cost per unit. And the power's got to be in kilowatts and the time has got to be in hours. So there's nothing should catch us out in this question, because that's what the power and the time is actually in. Have a quick scroll back to this. So we can see that the power, the average power of the cooker is 2, and it's used for 6 hours a week. The average power of the immersion heater is 3 kilowatts, and it's used for 12 hours a week. So going back to the calculation, the cost to the cooker is very straightforward. We times the power by the time by 20. 2 kilowatts times 6 hours times 20 pence is £2.40 or 240p. For the immersion heater, the cost is equal to 3 kilowatts times 12 hours times 20p. Times those together and you get 720p. And then obviously what we're interested in is the difference. And the difference is about £4.80. not about at £4.80, £4.80, which is about £5. And so Habib was actually correct. Part B, the electricity that Alice and Habib use comes from the national grid. The national grid has many power lines at high voltage. The national grid uses two high voltages, 4 times 10 to the 5 volts and 2.75 times 10 to the 5 volts. So those values are likely to be important, so I'm just going to underline them. Both voltages are used to transfer 2 times 10 to the 9 watts of electrical power. Calculate the current, so you want to know the current in the power lines at each voltage, and explain why the higher voltage is better for power transmission through the national grid. Okay, so they've broken the calculation down into 2 steps for us. The first step, at voltage of 4 times 10 to the 5 volts. Now the equation that links the things that we're looking for, we need to find the current. So the equation that links power, voltage and current is on page 2. Power equals voltage times current. We need to rearrange it so that the current is equal to the power divided by the voltage. Then we put our numbers in. So the power is 2 times 10 to the 9. And we've got to divide it by the voltage, which is 4 times 10 to the 5. Put that into a calculator and you get the current as 5,000 amps. Then moving on to the second calculation. So we use the same equation. Current equals power divided by voltage. The power is the same, 2 times 10 to the 9, but this time the voltage is 2.75 times 10 to the 5. And that's equal to 7,273 amps. So our explanation, which is why a higher voltage is best. Higher voltages are best because lower currents are produced and this reduces heat losses. So remember that whole thing about transformers, about transmitting energy. Anytime a current flows through a wire, you will get a heating effect that will produce heat, which will be then escape to the surroundings and be lost to the surroundings. So we want to reduce that as much as possible because we're paying for this and it's inefficient, and so therefore we want to use as low a current as we can, and so that's why we step those voltages up. And that brings us to the end of this section, section B. So look out for the next video for section C, which will be about P3.